Okay. Good morning, everybody. We are starting a new part of the course today, which we're excited about, which is we will begin to talk about how to learn to act in an uncertain environment. As if you think about it, so far we've been building models that are either predictive or that are trying to make sense of unsupervised data, and we haven't been explicitly thinking so much about the type of things we might be wanting to do with those models. And one obvious thing that we want to do when we think about AI research, but also when we think more generally about the problems that we might be trying to solve through technology, is to make decisions in an uncertain environment.
Yeah, absolutely. And I think there's a really cool build here of first we have to learn how to just organize our data, and that's unsupervised learning, and how do we compress it into a useful representation or organize it somehow. And then usually from that, we want to be able to think about what might happen in the future based on certain actions. So we might want to model of the world, and that's where the supervised learning comes in. That, hey, if I do X, Y might happen. But if I do some other action, X prime, then some other outcome might occur. And now we're finally getting to the place where all of it comes together to the thing that we actually want to do, which is use these models to make some decisions that cause something good to happen.
Make decisions, and there are lots of different ways then to go about modeling the world in order to learn to act, and we'll talk about some of these. I know this is something you work on in your research as well, Finale, and you work on things in your lab that are related to sequential decision making. Just wondered if you wanted to share an example of the types of sequential decision problems that you think about.
For sure. And I mean, obviously, David, you work on a lot of these too. It's kind of interesting that this last part of the course is like that it feels like we're compressing so many ideas in, because this is the stuff that we work on, and there's so many pieces. But yeah, so the sort of questions that we are often looking at are like how to make decisions in medical decision-making scenarios. And here, once you put someone on a ventilator, or once you start a certain type of IV, that effect might last for a while, and you have to think about what the effect might be in the future. Or if we're thinking about HIV treatments, maybe there's a way to reduce someone's viral load now, but that will cause some sort of cross-drug resistance that really leaves them screwed over a year from now, when this drug stops working and all of it, a bunch of other drugs also stop working because of cross resistance across different meds and such like this. So these are not only decision-making problems, but they're sequential decision-making problems, where there's a set of decisions that have to be made to optimize for long-term future gains.
Yeah, so this is a very vibrant area of AI and machine learning at the moment. We'll be talking about reinforcement learning, and some would say that reinforcement learning is AI complete, meaning that if you can solve the RL problem, you can solve the AI problem. Now, that's an extreme statement, but you hear people say that. So there's a little bit of motivation for what we'll be studying. Just before we get into the material, we also just wanted to comment that there's been that the written notes from Tuesday have been slightly clarified from lecture.
There's a couple places that were unclear, and also I had an error in my max part of the Viterbi algorithm, finding the max sequence. So the PDF is correct now, but the recap still needs to be updated.
Okay, great. So what I want to do is I want to jump here. Also, just do a quick recap of what we saw on Tuesday. We were talking about hidden Markov models. I'm using S here, where we were using Z, but again, the key idea is that there is a hidden state that is unobserved, and that what we observe are a sequence of observations. And as you will know from Tuesday, the Markov assumption, hence the hidden Markov model, is that once we're in state S, then the states and observations before state S are irrelevant to understanding the future. So it's This state is sufficient to understand what will happen into the future. That's the Markov assumption. And we'll be talking more about that today when we talk about Markov decision processes. One example of using HMMs would be for automated vehicles, where the state of a vehicle is either empty or parked or waiting or turning. And the observations could be things like the position of the vehicle, velocity, size, color, number of passengers. And of interest here and an application of HMMs would be to ask, what is the probability that a vehicle is parked given the sequence of observations? I think I talked about this right at the start of the semester. This kind of idea that if you're designing an automated vehicle system, it's really useful to know whether the vehicle to the right of you at a junction is waiting for you or is parked. And that will affect the way you decide to drive. The other example I wanted to mention of HMMs before we jump into the main material for today, and this was really the application that launched the entire field of hidden Markov models, and the algorithms that we use today that we saw 2 days ago is for speech recognition. So for speech recognition, your observations are the frequencies that you're actually measuring, so the vocalizations that you're measuring. Think about it as maybe represented as a high-dimensional vector. And the states are the little sounds, the sounds like eh or m or n or k. So the states are the phonemes, which when put together form a vocalization of a word. And you're trying to, for example, from the frequencies that you can measure, you're trying to ask, what is the most likely sequence of phonemes given the observations? So this is the problem we talked about right at the end of Tuesday. She's going from a sequence of observations, say, okay, I think now that I've seen all of that, the most likely utterance is this. So those are just 2 HMM examples. But as I said, today we're going to be turning now and talking about reinforcement learning. So we're right at the bottom of our stack here. I'm going to be thinking about learning problems where you have a notion of a state. This is something you can observe about the world around you. You have a decision to make, you have an action to make. And the type of data you have available to you is state, action, reward. State, action, reward. So you keep acting in a world, and as you take actions, you receive a reward from the world. And the learning problem is going to be to learn a behavior that provides you with high reward. That's going to be the reinforcement learning problem. Of course, this is just an overview. We'll get into all the details. I talked about some examples right at the start of the semester. You can imagine using RL to learn how to get these humanoid robot things to walk around or to flip a pancake. Or I just was reading a research paper this morning on using RL to learn a particular behavior for autonomous vehicles, where in this case, the behavior that they're looking to learn is whether or not, if you're this car at a road junction, you should creep forward just a little bit because you recognize that this vehicle is occluded by this vehicle. Just as an example of the types of things, this is a behaving in an uncertain world and using reinforcement learning to find a way to address that problem. So what are we doing? We're now talking about what I'm calling learning to act. So we're thinking about having agents that are embodied, meaning that they can take actions in a world environment. We're going to get into the details on this, but this is a useful picture, I think, just for you to conceptualize how we'll think about it. There are states that describe what you need to know about the world that you're in. We'll be assuming for the purpose of our discussion that the state is observable to the agent that is acting in the environment, the agent takes an action. So the blue boxes here are the actions. The state coupled with the action induces a reward. That is, the rewards are in the diamonds here, and then leads the state and the action lead to a new state. So notice this is like the graphical model pictures that you've seen so far. These circles are indeed random variables, and the way to read the arrows into these circles is that the random variable here has a distribution that is conditioned on the state and the action. Notice we've got additional elements though. We've got these square boxes that are representing decisions of agents. We've got these diamonds that are representing rewards agents receive in the world. And our data is a sequence, SAR, onwards and onwards. State, action, reward, state, action, reward. We'll call this a Markov decision process. We'll formalize this. And the target of learning is a policy. A policy describes a way to act in every state. So it says you can kind of look at the state, you say, okay, this is the state, here's the action that I want to take in that state. That's the policy. Let's talk about a few examples to try to focus our ideas. One example is a house cleaning robot where the states are the physical location of the robot, the objects in the environment. You can think about having a robot tidy your room if you like. The actions are moving or picking something up or dropping something, and the reward might be +1 if you pick up dirty clothes, -1 if you break a dish, -5 if you move the carefully piled stack of CS-181 notes, etc. And then the transition model would describe both the uncertainty in the environment. Maybe your friend comes in and your friend is viewed as a stochastic randomized part of the environment and may move things around. Or maybe your actuator, the way you take actions, is not perfect. And the robot tries to pick something up, but it breaks it. Or we can think about Go. You will probably know that RL, reinforcement learning, was used in 2016 to beat the world champion at Go. Here, the states would be the board position. The actions would be move a piece. The reward would be a +1 in a win state, a 0 in a draw state, a -1 in a lose state. Notice that in a game like this, you only get rewards a long way into the future. You can think that you have to act for a long time without getting rewards that guide your learning problem. And that's one of the things, this kind of notion that rewards might be pushed into the future is one of the things that makes reinforcement learning a challenging problem. In this case, the transition model that describes how states become new states would be a combination of the rules of the game and the response of the other player. Last example I have for you, I know we talk a lot these days about chatbots, and I was talking to a Harvard College student just yesterday who's about to start an internship with a firm that is developing AI for chatbots using GPT-3. And you could think about the state as being the summary of the conversation so far, the action as the words to utter, the reward as +1 if you solve the problem, -1 if you need to go to a human helper, and -10 if the caller hangs up angry. And then the transition model is the effect of the words that you utter as a chatbot on the state, and the next words or action that are taken by the caller. So hopefully you can see from these examples that the problems we're talking about today are very rich, very general, very powerful. You could study the topics we're going to talk about for these 3 lectures over a whole semester, so we won't be able to get into many of the details, but we want to give you a look at this because it's really becoming an important part of the field of machine learning and AI. Are there any questions so far before we jump in and get a little bit more technical? Yeah, Sharon?
So I saw that like in the different examples, there were different numbers of like plus or like different numbers of reward categories and different numbers of like you did this wrong category. So like, could you technically have as many of those as you wanted, or is it like more feasible to just have like a couple of those?
Yeah, you're getting to a really important point, which is honestly not very well understood, which is the problem of how to design reward functions. So I guess in the early days of reinforcement learning, we used to typically insist that the rewards come from outside of the agent. So it might be you make some money, or somebody gives you a gold star, or you're given some food. Over the past, let's say 10 to 15 years, there's been a lot of attention to engineering the reward functions such that you can somehow guide the agent more effectively. There's this topic of intrinsic rewards. And if you think about it, one thing that's been observed, if you think about the way we receive our rewards, I mean, it's true that we're living in an environment, and ultimately we're sensing and we're feeling reward from our environment. But in a sense, all rewards are internal. It's things like dopamine in your brain that actually trigger you to feel happy or sad. And there's a lot of effort in AI now to try to engineer reward functions that can lead learning to be more effective. Thanks for your question. Okay. So let's talk about then what we're going to do for the main topic today, which is Markov decision processes. And again, the picture I want you to have is an agent, a world. Our agent is taking an action in the world, and the world is somehow generating a next state and a reward. And here, think about little t as the time period. Maybe just a note about notation. We've been very careful through the whole semester. We've tried to be very careful. I think we've generally succeeded around notation. For this part of the course, the notation will change because we're doing different things now. But at the same time, I think it will be fairly natural. In particular, I'm not generally going to be talking about vectors. You can think about little s as being as taking on a value from a set of values that represents a state. That could, of course, be encoded as a vector, but we generally won't need to think about things that way. So just, I guess, apologies, the notation might somehow abruptly look a little bit different from things that you've been used to seeing, but at the same time, I think it will be reasonably accessible. I think it's useful always when we're doing machine learning, just to think about what the data is. As I said, in this case, the data is state, action, reward, state, action, reward. And let me define for you a Markov decision process. It's going to be defined by four things, S, A, R, and P. We'll have states S. Think about these as the possible states of your room. Actions, A. think about these as the possible actions that the robot can take. It can pick something up, it can move. Reward function. R of S and A, which gives you a reward, a number, for taking action A in state S, and then a transition model. Which gives you the probability of next state being S prime, given that you take action A in the current state. So the robot tries to pick up a dish. The next state might, with some probability, be it's holding the dish and the dish is no longer on the floor, or with some probability, the dish is now broken and there are bits of the dish on the floor. We need to talk about a policy. This is the solution object. So policy pi, which defines for each state the probability of taking action A given in state S. That's a policy. Notice that I'm allowing for a randomized policy. I'm allowing for this to be putting probabilities on more than one action. We will sometimes specialize that and just deal with policies that are non-randomized, but in general, policies may be able to flip coins and with probability 0.2 move left and with probability 0.5 go forward, for example. And with probability 0.3 do something else. I want to write down explicitly the Markov assumption. We've actually already made two assumptions by writing down the model this way. One assumption is a Markov assumption, or the Markov assumption, and one assumption is a stationarity assumption. I think it's useful just to write these down. So the Markov assumption that we've made here is that this thing can be simplified as this. This is what I emphasize for HMMs, same type of idea, that if you know state ST, then you don't need to know all the previous states. And if you know state ST, you don't need to know all the previous actions. Current state tells you everything you need to know to understand the effect of an action you take now on the transition to a new state. This is the Markov assumption. Notice that I wrote P sub little t here. You see there's a little t here? Whereas up here, I didn't write a t. Here, my probabilities were independent of time. That's our stationary or stationarity assumption. So that assumption says that this can be written as a probability distribution that does not depend on time. So now I've dropped the little t from the distribution function. Okay. So these two assumptions were implicit in being able to write down the transition model as a time invariant and a conditional distribution that only depends on the current state and the current action. Any questions? Okay. Now, so there's an MDP. So let's remember, let's just write that down in shorthand again. Remember, an MDP will carry with it these four things: a set of states, a set of actions, a reward function, and a transition function. There are two flavors of problems that we're interested in when we are working with Markov decision processes. One problem is a planning problem, and one problem is a reinforcement learning problem. I want to be precise about what these are. So in one problem, your input is the description of the MDP, and your output is the optimal policy. By the way, notice that I wrote down a simplified MDP where I assumed the actions and the states were discrete. In general, continuous state spaces are very challenging to handle. In general, continuous actions are relatively challenging to handle, but can be handled more readily than continuous state spaces. We are just going to assume that the state space and the action space are discrete. When things are discrete, it means that I can describe the reward function easily, the transition, I can describe the transition model easily. So my input is easy to describe. And then you have kind of a well-defined computational problem. Okay, here's the input, S, A, R, and P. Go ahead and compute the optimal policy. That's the planning problem. The reinforcement learning problem is the input is access to the world. You're able to move around the world, take actions, receive rewards, observe next states. That's how to think about the input. And the output is kind of actions. I mean, it's literally a reinforcement learning agent is literally going to be moving around in an environment, taking actions. You could think about this kind of over time as learning a policy. Because over time, it's going to learn, hopefully, how to behave effectively in the environment. But imagine you've just unpacked your new fancy room cleaning robot from Amazon, and you let it loose in your room, and it starts doing stuff, and it has to learn from feedback, either which may be given by you. You might be like, that was good, that wasn't good, that was good, that wasn't good. And it's going to have to learn over time what's good. Okay, now we need to be precise about what I mean by optimal policy. So let's talk about the objective. There are two variations on this. One is an infinite horizon problem, and one is a finite horizon problem. Infinite horizon is you are living forever. Finite horizon is you are not. If you want to think about it for the robot, infinite horizon is somehow it's a rechargeable robot that's able to recharge itself. If it's a finite horizon problem, the robot only has so much power and at some point will no longer be able to move. In the infinite horizon problem, we're interested in finding a policy that maximizes the expected sum from time period 0, we'll index time starting at 0, up to infinity, of the discounted reward. Let me say a little bit about this. So first of all, this expectation here is taken with regard to actions that are sampled according to the policy. there are two things that are random in this expectation. One is actions are sampled according to policy, and one is states are sampled according to the transition model. Gamma here is our discount factor, which we'll think about as being in 0, 1. Notice I'm writing the end of this interval as open. I don't want to think about gamma actually being equal to 1. The role of gamma is going to be to discount the future. Notice that if your rewards were 3 every time period, then you'd have gamma to the 0 times 3 plus gamma times 3 plus gamma squared times 3 plus plus plus. And this is equal to, of course, this is just 3 plus gamma 3 plus gamma squared 3 plus plus plus. And this infinite sum, hopefully if you remember your series from some math class you've taken, if I give you 3 plus gamma times 3 plus gamma squared times 3 plus gamma to the 3 times 3 all the way up to infinity, as long as gamma is on 0, 1, that's equal to 3 over 1 minus gamma. So the nice thing about using a discount factor is that as long as the rewards are bounded, in this case my reward was just 3, as long as the rewards are bounded, then the infinite discounted sum is also bounded. Notice that as gamma gets closer and closer to 1, so think about gamma as 0.99. When gamma is 0.99, this is 3 over 1 minus 0.99, 3 over 0.01. So this becomes a big number. So as gamma gets closer to 1, you get more patients. And as gamma gets closer to 0, you get less patient. I also just want to say a little bit more about this notation here. This is shorthand for something we could have written that's a lot more complicated. But I want you to read this R sub t as a random variable that is induced by the policy you're following and the transition model in the world. Okay, that's how to read this RT. And in particular, maybe we can try to write down kind of a generative view on it. Kind of a generative view is A0 is sampled according to your policy from some initial state. That leads to the rewards at time period 0, and then leads to state 1 being sampled according to the transition. Then we would sample A1 from the policy given. Yeah, sorry, I should have written that as a given up there. Policy given S1, and then the reward would be the reward given that we've just taken action 1 in state 1, S2. Yeah, so you can kind of see how we're using the randomized policy, the transition model, to kind of induce this random sequence over rewards into the future that correspond to a policy. And then the infinite horizon planning problem is to find a policy that maximizes that expected discounted sum into the future. Okay. And then this case is a lot simpler. This case is just this. So now let's say my time horizon is capital T. So because now I have a finite time horizon, I don't need to discount. Like, it's well defined just to say the sum of the rewards. You could still choose to discount if you wanted to. It's a modeling choice. but you don't absolutely need to. Yeah, and as we said, this is all just for an example. Any questions? Yeah, just to assume a non-finite sum is one way to answer it. It's also arguably realistic because you know, you may care more about recent things and things far into the future. You may have a lot more uncertainty about your model as you get further and further into the future. You may be dealing with the probability of end of life for various reasons. You may be dealing with inflation if this is a economically oriented problem, and so forth. Okay. But mathematically, it's crucial. There's actually one other thing you can do, which we're not going to dwell on. You could also take the lim sum average rewards. Don't worry about that if you don't know what that means, but that's another thing you could do. But we will use discounting, which tends to be easier to work with. Okay, so I want to talk for the rest of class about how to use, so we're only going to talk about planning today. And I want to talk for the rest of class about how to use something called value iteration to solve the planning problem. We'll talk about using value iteration in both the finite horizon problem and the infinite horizon problem. So let me define, let's talk about the finite problem. Let me define this to be the total value from state S under the optimal policy with T steps to go. And I want to emphasize that the reason I'm writing this in a parenthesis underneath rather than just T is that this is normally when we index by T, it will mean the T step. In this case, this is T steps to go, which is why I'm writing it with the parentheses. So V star 1, V star sub brackets 1 would be the last action you will ever take. Now, I think many of you will have been familiar with dynamic programming. And there's a principle of optimality that we can appeal to in thinking about how to solve the finite horizon planning problem. Notice, maybe just to spend a second on this, this object is going to be very useful for us. If we can calculate the total value from state S under the optimal policy with one step to go, then we can use that, we hope, by working backwards from the end of time to the start of time. We can use that to understand what to do with 2 steps to go, and then what to do with 3 steps to go. That's going to be the design pattern here. And we'll be using this principle of optimality, which says that an optimal policy consists of an optimal first action, and then 2 followed by an optimal policy from the successor state. It's probably intuitive to you. It says that the optimal thing to do is going to be a combination of trying to understand what's optimal to do now, and then continuing from the state you land in to follow the optimal thing forward from that state. And we can write that down formally. This now is the idea of value iteration. Base case with 1 step to go is you just take the best action. You don't have to worry about the future. This is defined for every state. Notice this is a function of state. This says in every possible state, all possible configurations of your room, with one step to go, the total value forward is given by taking the optimal action, just considering that current state. We're not worrying about the future. The last thing you can ever do, what do you want it to be? Your battery's about to run out. Inductive case. So now let's use what we've solved about fewer than t plus 1 steps to go to solve for t plus 1 steps to go. And here's where we use the principle of optimality. Let me pause so you can all write this down, those of you that are writing. So it's v star t plus 1s. This is our value with t plus 1 steps to go, is the maximum action to take now, considering the reward for different actions now, plus I think about the distribution over states that I land in next, and then I think about the continuation value. I think about at that point, I would only have t steps left. But assuming that we're working inductively back from 1 step to go up to multiple steps to go, the idea is that I've already solved for this, and then I can plug this into the recursion, and I can compute the right thing to do in every state with t plus 1 to go. Any questions on this idea? Okay. I think what we'll do is we'll work a little example of this, and then we'll take a short break. So let's just work a little example. Again, here's my recursion. Yeah, S prime is the next state. Just the very next state. So let's do a little example. This is a world with 5 locations. Also, I think it's helpful to think about there being a location with 0 reward that we reach after taking any action from this state or this state. What are the numbers that I've written down here? These are the rewards for taking any action in a state. What are the actions? Left or right? So there are 6 states. The special state where you get no reward and you're unable to leave. These 5 states. In this state, which I've labeled -1, any action you take, left or right, will bring you a reward of -1. In this state, any action you take, left or right, will bring you a reward of 5 and will transition you to this absorbing state. The same with this 10 state. Any action you take will bring you a reward of 10, will take you to the absorbing state. In these three states, these -1 labeled states, if you take a left action, you move left. If you take a right action, you move right. And we'll think about this as being horizon t equals 3. Remember, we index from 0, so you get to take 4 actions before the end of your battery power. I think you can kind of see what the optimal policy would be here. You can see the optimal policy would be to move left, move left, move left. Kind of in these two states and in this state, you have no choice of action. Any state, any action you take will bring you the same rewards and will either move you here or leave you here. But you see, like if you're here, it's better to move left and get a total reward of -1, -1, -1 plus 10 is better than moving right and getting a reward of -1 plus 5. Okay, so now let's just do our backward induction or our value iteration algorithm. And we start with 1 step to go. And I'm just going to draw the absorbing state off to the left here. And remember, with 1 step to go, we're just writing down the values of the maximum myopic action in that state. Yeah, remember, with 1 step to go, this is just max A R S A. So you would get these values here. So it's like you're in this state. It's the last step you can ever take in the world. Doesn't matter. Left or right, reward will be -1. So that's the number that we write there. But once we've got that, now we can use our inductive step and we can figure out the 2 step to go values. Now the 2 step to go values for these states will again just be 0, 10, and 5. Because again, you have no choices of how to act. Here you'll get 10 when you act, and then you'll get your continuation value, which will be 0 because you'll be here. You'll have 1 step to go and you'll be here. So you do 10 plus 0 and you write 10 here. But we have a little bit of work to do for these 3 states. And let's think about this state here. Let's think about this state. So for that state, if we take action left, then we have to think about what this will be. And it will be -1. This world is deterministic. So we just have to think about the value with 1 step to go in the state that we land in if we move left, which we read off. So we're like, okay, it's kind of like you'll read off this 10 because you already calculated that. You know that if with 1 step to go, you're in that state, you know you have reward of 10 you can get cumulatively. Action right would be -1. Okay, with 1 step to go, you know you'd only get -1 from this state. So -1, -1 equal -2. And then we would take the max of these two. Max of those two is 9, so we'd write 9 into there. Makes sense? And then here, it's the max of -1, -1, or -1, -1, so we'd write -2. And here, it's the max of -1, -1, or I could move right. If I move right, then it's -1 plus 5, which is 4. So this recognizes that the right thing to do with 2 steps to go in this state is to move right. And then we just keep going. We can do this a bit more quickly now. This again will be 9. Oops. Now notice that this action, this state's now more interesting. Left is now -1 plus 9 is 8. Right is -1 plus 4 equal 3. So 8 is better than 3. So write that in as 8. This one here will remain at 4. And then the last, now with 4 steps to go. Oops. Now this state is interesting. Oh no. And action left will be -1 plus 8 equals 7. And action right will be -1 plus 5 equal 4. And 7 is better than 4, so we write in 7. So that's the idea of value iteration. I just want to note that you can now read off your policy. The way to think about how to extract a policy from these optimal value functions is that the optimal policy, let's first of all define it. The optimal policy we'll write as pi star TS. This is the action to take in state S, T steps to go. And it's going to be calculated by the same expression as above, except now it has this argmax instead. And in particular, you can kind of go back through what we did, and you can recognize that as we were doing the forward pass to calculate the values, we could have also been annotating the optimal thing to do. So maybe initially it's left, 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 left. Remember in these states, any action is equivalent. And we'll just say arbitrarily decide to initialize these actions to be left. Here, when we did the argmax here, we picked left. So that would be a left action. Here, let's say we're arbitrarily keeping it as left. Notice here, when we did the max, we've now set this to a right action. So you see how we're keeping track? We could keep track if we wanted to of the optimal actions that we're taking. And down here, we learned that we should be going left here in this state. But you could also just read it off. Once you've calculated all of these numbers, it's easy to read off what the optimal action is. Are there any questions? Yeah, Blake.
I'm just wondering why the optimal policy we're writing with the T steps to go index, because shouldn't it be the same at any time step after we've finished our value iteration? Like the
right. Yeah, it is going to depend on time, but just to be consistent, let me write T plus 1 rather than T. But it is going to depend on time. I'll explain why. Um, for example, you can see it here. If you're in this state with 3 steps to go, you should move right, because within your time horizon, you cannot get over here and take the action that will give you the reward of 10. Whereas if you're in this state with 4 steps to go, you should move left because you have enough time to be able to get the higher reward. So in a finite time horizon problem, the time to go affects the policy affects the actions you should be taking. In an infinite time horizon problem, there will be no T. The state tells you everything you need to know which action you should take. So it's because we're in a setting where there's a deadline that it affects the actions you should take. And in particular, to figure out what to do for different times to go and in different states, you don't just use these numbers, you need to use all of these numbers. Like these numbers together with, actually these numbers here, together with the reward in the world, will tell you which actions to take with this time left. And these numbers together with the reward in the world will tell you which actions you should take with this many steps left. So you use all of the numbers to figure out your policy. Did that answer your question, Blake?
Yeah, I think so. So it seems like we're keeping track of the optimal policy at each value iteration, and then, but what we're really interested in then is the optimal policy that we get at the very end, like after we have convergence, right?
Yeah, I think you may be slightly confusing what we're doing here for the finite horizon problem and the infinite horizon problem. Don't think about this so much as about convergence at the moment. Think about this as this is the correct value for the optimal thing to do with 2 steps to go. Like it really is true that if you're in this state with 2 steps to go, the best reward you can get is -2. You have no way to get to either goal. These are the correct, like this 4 here, that really is the correct cumulative rewards with 3 steps to go. If you're in that state, you don't have a chance to get over to the 10 reward goal. So by convergence, if by convergence you mean once we've got all the way through to the start of time, which is here, this is the start of time. Yeah, that's convergence. And then you can begin to now read off, okay, I'm going to look here to see what action to take now. And then I'm going to be with 3 steps to go. And I'm going to look here to see which actions I should take with 3 steps to go. And then I'll land in some state with some distribution, and I'll look here with 2 steps to go. That makes sense. So you look back at the time.
Yeah, okay, I got it. That makes sense. Thank you.
Okay, yeah. All right. So I'm just thinking about time. Finale worried. You warned me, Finale, that this stuff takes longer than you think it's going to take. Okay, so I think we'll just keep going, but I think the upshot is that we may not be able to do concept checks because my concept checks are on material that I'm not sure we're going to quite get to before the end of session. I think that's okay. But I think I'm just going to keep going if you're all okay. We won't take the promised 2-minute break. I just want to make one last comment about what we've just been doing, which is the computational complexity of this. Let me just write it here. So we just want to understand how much computational work we have to do this calculation here. And it's order T, however many time steps there are. The number of states S, because in every time step, with every time to go, you have to do this calculation for every state. The number of actions A, because you're taking a max over the number of actions. And then you have to do the summation here, and the summation sums out over as many states as are reachable. See how actually we only care about the states S prime that have some non-zero probability. And so that I'm going to use L. I'm going to write L to be the max number of states that are reachable from any state under any action. Okay. So again, every time to go, you have to do for every state, for every action. And the new thing I've added is this L. You only have to take this summation over the number of reachable states. So in our example, in our grid worlds here, L equal to in this grid world. Because you can only ever reach one of two neighboring states from the state you're currently in. All right. So I want to start talking now about the infinite time horizon case, which is the more typical case. And also a little bit more elegant in terms of the solutions that we can find. And again, we're going to think about value iteration. For the purpose of discussing this is we'll assume a deterministic policy, which I'm going to write as pi. Also, by the way, good news. I think we will do the concept check because I think Finale is right that we do know enough to do it. So we will do a concept check in around 4 minutes, I think. In the infinite time horizon case, I'm going to write my policy deterministically, which will just point to an action, a particular action. So I'm just using this new notation. This is just the action we take in state S. This is actually without loss of generality. You can show that it's sufficient to consider deterministic policies in the infinite time horizon case. And I want to define an MDP value function. This is an important object. It's the expected discounted value from policy pi in state S. So you're following a policy pi. That's what this notation is denoting. And I'm writing this capital V, which I want to denote the expected total discounted rewards according to my policy forward from that state. And I want you to notice that you can decompose this in a nice way as the reward now plus the discounted, because this will now be one step into the future, sum of the probabilities of next states you might reach for the action you've just taken times the value function in those next states. I think this is natural, I think, given the equations we wrote down for the finite case. So it says that the value of a policy is the immediate reward plus the discounted expected future values. And what we can now do is we can define what it means to have an optimal policy. In this infinite time horizon world. And it's the policy pi star that maximizes the value function. Interestingly, the same policy pi star will simultaneously optimize this from all possible states. Okay, so we'll be looking for a pi star that optimizes from all possible states. Remember that that's maybe not that surprising because the policy picks an action dependent on the state that it's in, and the rest of it is following from the principle of optimality. And I think where I want to leave the discussion, and we'll go to the concept check, is I just want to point out that, well, yeah, let's just define the optimal. Let me define the optimal value function. So this is the value function corresponding to the optimal policy. And this is defined as this object. That's just the definition. It's the value of the optimal policy. And when we come back next class, we're going to be working on solving this. And we're going to solve it by writing down what's called the Bellman equation, and then running value iteration using that equation. But I think what we'll do now is we will talk about the concept check, because I think we do know enough to talk about the concept check. So here it is. You're in an infinite time horizon. This is the grid world. This is the starting location. There are two goals, goal 1 and goal 2. Discount factor is 0.99. You have a perfect actuator. Here you can move left, right, up, down. There is a cost minus C for taking an action in any state. The cost could be 0, but it could be 0.1 or 0.01. Crucially, these goals are what I'm calling sticky goals. What's the sticky goal? It means that if you ever wander into G1, you will never leave G1. And every time you take an action in that state, so you're just always in G1 now, and every time you take an action, you'll get a reward of 0.1. So you'll get an infinite stream of 0.1 actions when you get to this state. And in this state, you'll get an infinite stream of 0.2 rewards when you're in this state. See, so wander around the world trying to get to G1 or G2. When you hit one of these goals, you're stuck there forever, and you either get an infinite reward stream of 0.1 or an infinite reward stream of 0.2. So then there are 4 questions. The first question asks you whether C affects the optimal policy. The second question asks you whether scaling all rewards, including the cost C by alpha, affects the optimal policy. The third question asks you whether changing the discount factor to something close to 0 affects the optimal policy. And the fourth question asks you whether, if we redefine the reward to depend not only on the state and the action, but also the state that you land into. And this can sometimes be, by the way, a more convenient way to define the reward. Maybe you're that robot, you're picking up a dish, and you want to distinguish between you break the dish or you don't break the dish. And so you want to write the reward down that way. But here what we're saying is, suppose that you rewrite the reward as the current reward plus a discounted quantity for some function phi applied to the next state minus the function phi applied to the current state. Suppose you use this as your reward function, then the question is whether the optimal policy changes. So that's what we're going to go ahead and do. And let's share the URL with you. And generate the breakout rooms. which, let me see, oops. No, I think I messed it up. Oh no.
I don't know how to rescue them.
I think what's happening. I think we have breakout rooms, but I think there are more people per room than I would have liked. But I think they're, oh, and they're also closing in 36 seconds. No, I messed up the breakout rooms.
Wait.
I wish there was a way to just not have them
And
close,
now they're-
right? like an undo. Huh. Okay.
oh no. Now they're counting down and they're all going to be pulled back.
Yeah. Hmm.
Crap. I'm so sorry. That was bad. Let me try again. Sorry about that. Okay, let's try again. All right, welcome back. So I thought this would be the best way to walk you through this. So does C affect the optimal policy? Most of you got this wrong, interestingly. Most of you said yes. Actually doesn't, because well, it depends how you think about it. If you were thinking that you only incur cost C when you're outside of the goals, which I guess now I realize I wasn't precise about that, then your answer is correct. If you were thinking that you incur the cost C also while you're in the goals, then your answer was incorrect. Because if you incur cost C every time period, then you can factor it out like this. I'll post this so you don't need to scribble this down. We'll make sure this is on the website. But things factor out, and the discounted sum of the C's is a constant. So I was imagining at least that you incur the cost when you're in the sticky goals. If that's the case, the answer is no, it does not affect the optimal policy. The next question was whether scaling rewards by alpha affects the optimal policy. You all got this right, and that's the math for why it doesn't. Almost all of you got that right? The alpha just comes outside of the expected discounted sum for any policy. Next question was whether changing the discount factor from gamma 0.99 to gamma 0.1 affects the optimal policy. Most of you got this right. There were a couple of unsures. The way to think about it is that, and here's the math just to check, but the way to think about it is that when you're patient, you have more value for going that extra step. So you have this gamma to the 5, and then getting your infinite sum forever of 0.2. I'm writing this down here as though the cost is 0. But when gamma is 0.1, you have more value for immediately getting that 0.1 rewards after 4 time steps than you do for incurring another 0.1 discount and having your 0.2 rewards being pushed out into the future. That's the intuition. So as you become more impatient, you prefer to go to the closer goal. And then the last question was whether the potential function here we're using, the phi of s prime minus phi of s, changes the optimal policy. Most of you got this right. There were a few not sures. You shouldn't feel bad if you weren't sure about this. I didn't even have the time to really explain this SAS prime idea. But the way to see it mathematically is that now the reward function looks like this, and we can telescope this out. So for time period 0, it's this quantity plus the new terms that we've added. For time period 1, it's this quantity plus the new terms that we've added. Notice there's a gamma in front of both of these because we're in time period 1 now. Time period 2, new terms. And then you see how this cancels with this, and this cancels with this, and so forth. And so everything ends up canceling out except for the initial phi term, which is just a constant. And so the answer is that doesn't affect the policy. And the reason that we talked about that is that that gets back to the question Cherry asked me actually right at the start of class, is that there's this idea of reward shaping in the literature, where if you can find a potential function that you can, for example, add and subtract in just the way I described, but carries useful information about the world, then that can speed up reinforcement learning without changing the optimal policy. So this kind of idea of being able to drag rewards around like that can be helpful to try to speed up reinforcement learning in the real world. I'm going to stop recording. Happy to hang out to take questions. Sorry, this was a little bit rushed.